Completing the square makes I quadratic visible. CardAHno went one dimension higher. He cut I cube, and its pieces encoded I depressed cubic. Can I quartic be solved by cutting the next object in the sequence? Yes. This tesseract will give us the depressed quartic formula. I segment measures length. Sweeping it makes I square, whose area is x squared. Sweeping the square makes I cube, whose volume is x cubed. One more independent sweep makes I tesseract. Its four-dimensional volume is x to the fourth, exactly the leading term of I quartic. I uniform enlargement is not the right construction. Expanding x plus h to the fourth creates 4hx cubed. But our quartic is depressed. It has no cubic term. Setting that layer to 0 forces h to be 0, and then the completion does nothing. We need I different cut. Instead, divide every independent direction into 3 lengths, u, v, and w. Call their total capital X. The same 2 cut positions pass through all 4 directions of the tesseract. 3 choices in each of 4 directions produce 3 to the 4th, or 81, 4-dimensional cells. Each piece is not merely an ordinary box. It is the Cartesian product of 4 intervals, 1 interval selected from each direction. Its hypervolume is the product of those 4 widths. Separating the pieces in this projection lets us see the cut, even though the cells themselves are 4-dimensional. The pieces fall into 4 multiplicity patterns, 3 pure cells, 24 with 3 equal widths, 18 split 2 and 2, and 36 with 1 width repeated. We will not chase all 81 individually. A more exact product view will group them cleanly. Pair the tesseractus 4 independent directions into 2 pairs. Each pair makes an x by x coordinate square. Their Cartesian product is exactly the tesseract. If I is I region in the first square and B I region in the second, I times B is I genuine 4-dimensional cell, with hypervolume equal to area I times area B. Cut either square into the same U, V, W grid. Its 3 diagonal pieces have total area S, U squared plus V squared plus W squared. Above the diagonal, the 3 unlike products total M, UV plus UW plus VW. The reflected half contains the same 3 areas again. Therefore, x squared equals S plus 2m. Now take the Cartesian product of the 2 grouped squares. The entire tesseract has 4-dimensional volume S plus 2m squared. The product regions give S squared, 4sm, and 4m squared. This is literal accounting of the 81 cut cells, not an assignment of values to vertices. Only m squared remains to be understood. Its 3 matching pairings total T, U squared V squared, U squared W squared, and V squared W squared. Its 6 crossed pairings occur in mirrored pairs. Factoring P equals UVW, those pairs total 2P times U plus V plus W. Since that sum is X, M squared equals T plus 2PX. We can now eliminate M. From the square, 2m equals x squared minus s. And from the crossed cells, m squared equals t plus 2px. Substitute both geometric relations into the 4-dimensional volume, collect the pieces, and move everything to one side. This is the quartic identity encoded by the cut tesseract. Compare the tesseract identity with x to the fourth plus px squared plus qx plus r. Matching the quadratic, linear, and constant terms gives s equals minus p over 2, p equals minus q over 8, and t equals p squared minus 4r over 16. Scale the squared slice widths. z1 equals 4u squared, z2 equals 4v squared, and z3 equals 4w squared. Their sum is minus 2p. Their pairwise product sum is p squared minus 4r. Their product is q squared. Therefore, by va-Hess relations, these three quantities are exactly the roots of the displayed cubic. So the geometric system is recovered by solving one cubic, followed only by square roots never I-quartic or sextic. Geometry has produced I-resolvent cubic, whose roots encode the squared slice widths. But naming that cubic is not yet I-quartic solution. We now solve it by Cartier-Hno's cut cube, use one cubic root to factor the quartic into two known quadratics, and solve both by completing the square. No equation above degree 3 will appear. Begin with the known resolvent. Shift z by minus 2p over 3, writing z equals y minus 2p over 3. The quadratic term cancels. We obtain y cubed plus a alpha y plus b a equals 0, where a alpha is minus p squared over 3 minus 4r, and b a is minus 2p cubed over 27, plus 8p r over 3, minus q squared. Write y equals m plus n. I cube, whose edge is m plus n, cuts into 8 actual blocks. Their volumes give y cubed equals m cubed plus n cubed plus 3mn times m plus n. Substitute this into the depressed cubic. Choose 3mn equals minus a alpha, so the entire term proportional to y vanishes. What remains is m cubed plus n cubed equals minus ba. Let capital M equal m cubed and capital N equal n cubed. Their sum is minus ba. Their product is mn cubed, which equals minus a alpha cubed over 27. So either cube volume satisfies I quadratic. Kc squared plus ba kc minus a alpha cubed over 27 equals 0. Complete the square. Kc plus ba over 2 squared equals ba over 2 squared plus a alpha over 3 cubed. Call this last quantity d alpha. Therefore m and n equal minus ba over 2 plus or minus the square root of d alpha. Take compatible cube roots of those two volumes. Choose the branches so that mn remains minus a alpha over 3. Then y equals m plus n, and one resolvent root is z equals minus 2p over 3, plus the cube root of minus ba over 2 plus square root d alpha, plus the cube root of minus ba over 2 minus square root d alpha. Cartier-Hno has now calculated z explicitly. Assume q is not 0. Then 0 cannot solve the resolvent, because its constant term is minus q squared. Set I equal to the square root of z. Geometrically, I equals 2u, so one cubic root selects one slice width. We do not need to solve separately for v and w, and we do not create I sextic. From here on, only square roots remain. Pair the tesseract's sign symmetry using opposite linear terms. Write the factors as x squared minus I x plus lambda and x squared plus ix plus mu. Matching the x squared and ex coefficients gives lambda plus mu equals p plus z, and lambda minus mu equals q over I. Therefore, lambda and mu are known. Their product is r because the resolvent rearranges to z times p plus z squared minus q squared equals 4 or z. So this factorization is guaranteed by the cubic we already solved. Set each quadratic factor equal to 0. In the first, add I squared over 4 to both sides. This gives x minus I over 2 squared equals 1/4 times minus z minus 2p minus 2q over I. In the second, x plus I over 2 squared equals 1/4 times minus z minus 2p plus 2q over I. Taking the two square roots of each completed square produces all four quartic roots. Define A alpha, beta, and dE alpha as shown. CardAH-NO's formula gives z, and I is square root z. Then the two completed squares give the four roots displayed below. This is I usable formula. Every quantity on screen is calculated from p, q, and are using square roots and cube roots. Take p equals minus 12, q equals minus 16, and r equals 0. Then A alpha is minus 48, B alpha is minus 128, and dE alpha is 0. CardAH-NO gives z equals 16, so I equals 4. The two known factors become x squared minus 4x, and x squared plus 4x plus 4. Completing their squares gives the roots 0, 4, and minus 2 twice. No hidden polynomial was solved. If q is 0, the quartic is already biquadratic, and the expression q over I should be avoided. Set capital Y equal to x squared. Complete the square in y, then take square roots. This gives x equals plus or minus the square root of negative p plus or minus square root of p squared minus 4r, all over 2. The tesseract gives one cubic resolvent. CardAH-NO's cube solves that cubic. One cubic root factors the quartic into two quadratics, and completing the square solves both. The construction is therefore I-complete method, not merely I-verification that four guessed expressions happen to be roots.